The next measurable factor of the aquifer is permeability. Okay. If the aquifer has to yield the water, then we say that its permeability should be very, very good. Okay. Look here, what I am going to do is, I am going to take an rock holding the water, or let me say a geological formation, that is aquifer, which is holding the water. Okay. What I have done here is, for the experimental purpose, I have taken a strip out of this rock structure and have written here. Okay. Look here, this is the datum line or the reference line. This is where we take section 1 and this is where we take section. Okay. At the section 1 I have inserted a piezometer, and at section 2 I have inserted another piezometer. The water enters this piece of aquifer or part of aquifer like this, and it exits like this. This is a schematic representation or a 2D diagram. You can see the entrance where the groundwater starts to get in, and this is the exit where the groundwater starts to get out. Okay. Look here. The first important thing you have to remember is the groundwater has very, very slow movement, that is its velocity is something around 1 meter to 500 meter per year. You can imagine the slowness of the movement of groundwater. It just only moves to the range of 1 meter to the 500 meter per year inside the aquifer, or from one aquifer to another aquifer. This is a very important thing you have to remember. Okay. Look here, I have written here Z1 and I have written it as Z2 here. What do you mean by Z1 and Z2? Z1 and Z2 represents the datum head at section 1 and 2 is represented as Z1 and Z2. Okay. Just the vertical height from this reference to the section 1 and the vertical height from this reference line to the section 2 is nothing but datum head. Clear? Now, I have written it as P1 by rho g and P2 by rho g here. Okay. These two represents the pressure head that is available at section 1 and section 2. Okay. You have already studied about the pressure heads, so I am not going to explain in detail here. You have studied about the pressure head difference, pressure head in the fluid mechanics. Okay. At section 1, the pressure heads at section 1 and 2 are P1 by rho g and P2 by rho g. Okay. The next comes, what is the velocity head at section 1 and section 2? The velocity heads at section 1 and 2 is represented as V1 square by 2g and V2 square by 2g. Okay. I have not represented the velocity heads at section 1 and section 2 because at initial stage itself I told the velocity of the groundwater is very less as it moves very slowly. That is why I have not represented the velocity heads here, because we are going to neglect it. Okay. Now what I am going to do is I am going to apply the Bernoullis equation to section 1 and section 2. Okay. So what does the Bernoullis theory or Bernoullis equation states? It states that total energy which is available at section 1 should be equal to total energy of the water or the groundwater. It should be same at the section 2 as well. Okay. So what all the energies available? One is datum or energy or head. We can express the energy in terms of head. We have expressed the energy in terms of head here. Okay. What are the total heads or what are the kinds of heads available here? The datum head, pressure head and the velocity head. Okay. We are going to apply the Bernoullis equation to section 1 and 2 here. Look here, P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g plus V2 square by 2g plus Z2, and at the end I am going to write it as H suffix capital L. What does this H suffix capital L represent? Look here, you can see the groundwater is flowing from section 1 to section 2. The basic thing is the water starts to flow from high energy region to the low energy region, right. So if the water has to flow from high energy region to low energy region, then you should understand that there is a energy difference, okay, or there is a head loss, and that is represented as HL here. Okay. Look here, since we have neglected the velocity heads, we will leave out that V1 square by 2g and V2 square by 2g from this equation, and we are going to write like this. Right. So what does this head loss represents, or the energy loss represents, or the energy difference represents? The difference in the energy between the section 1 and section 2. Look here. Okay. The next thing you should observe is, I am going to write an equation. Just observe Q directly proportional to HL and A by capital L. What does this equation represents? Look here, HL represents the energy difference. If the energy difference between the section 1 and section 2 is more, immediately the water starts to flow from section 1 and 2, therefore the discharge will be high. Okay. So if HL is more, Q is more. That is why I have written Q is directly proportional to H, right. If the energy difference or the head difference is more, the discharge will be more. If the area of this cross section is more amount of water flows and this discharge will be more. Okay. If the length of this aquifer is very large, the water takes lot of time to move from section 1 and section 2. That is why I have written Q inversely proportional to length. If length is more, discharge will be less. If length is less, the discharge will be more. Okay. Look here, what I am going to do is I am going to bring this A to the denominator of Q, and I am going to write it as HL by L. Look here, what does this Q by A represents? You all know Q is equal to A into V. V is equal to Q by A. This is the normal discharge equation which we have used extensively in the fluid mechanics as well as in the hydraulics. Okay. So I am going to replace this Q by A by V. I am going to write it here. V is directly proportional to HL by L, right. Okay. So what do you mean by V there? V is nothing but the groundwater's velocity or the velocity of the porous medium we say, or we will say it is nothing but Darcy velocity. Okay. Now, what does this HL by L represents? It represents the gradient of the potential head. Okay. I am saying as a ratio of HL by L. What does this HL by L represents? The gradient of the potential head. How? Just look at the diagram. You can see once you insert the piezometer, the water level has risen and it has been standing there. Okay. If when water is standing, we say that it possesses potential energy or potential head, right. So, the potential head difference here can be indicated as HL, okay, and this potential head is varying with respect to the length here. Look here, here the vertical height of the water standing is more. As we move down, the head of water or the vertical height of the water has reduced, okay, and it has reduced with respect to what? L. That is why we are saying that it is the rate of what? The potential head or the gradient of the potential head. Clear? Okay. Look here. So, HL by L represents what? Gradient of potential head. Okay. Now, look here. I have to remove this proportionality. What I am going to do is V is equal to minus K into HL by L. Okay. Why I have written minus K, I will tell you. Now, look here, if this distance between the two piezometers is less, we are going to indicate the distance between these two piezometers as dl, and the head loss is indicated as, or the gradient of potential head is indicated as dH by dEL. Okay. Now, there arises a question, why this negative sign? Difference of this loss of head in the direction of flow, that is why I have written it as minus, and this K is nothing but coefficient of permeability, or you can say hydraulic permeability. Am I clear? So, this V is called as Darcy's velocity and this K is called as hydraulic permeability, or you can call it as coefficient of permeability. This is the derivation which has been asked number of times, and this will be asked for 8 marks. I hope you understood. I hope I have conveyed about the Darcy's velocity, hydraulic permeability. Now, how do you define permeability? Permeability is nothing but the capacity of an aquifer to yield the water readily whenever necessary. Okay. We got the equation for Darcy's velocity. The equation for the Darcy's velocity is V equals minus K into dH by dL, right. Here the K represents the coefficient of hydraulic you can call it as hydraulic conductivity or coefficient of permeability, and this dH by dL represents hydraulic gradient. During this derivation, we had gotten expression Q by A equals minus K into dH by dl, right? So, from this equation I can define hydraulic conductivity or coefficient of permeability. Look here, K equals Q by A divided by dH by dl. Okay. Look here, you can define the coefficient of permeability or hydraulic conductivity as the rate of flow per unit area of the aquifer under unit hydraulic gradient. That is, the unit hydraulic gradient means dH by dl equals to 1. In that case, K will be equal to Q divided by A, or you can write K equals V. Okay, V means Darcy velocity. Okay, what is the unit of velocity? The unit of velocity is meter per second, but in the case of groundwater, since the velocity of the groundwater is very less, you are going to express in terms of meter per day or meter per year. Okay. So, if the groundwater's velocity's unit is meter per day, the same unit is applicable for what? Coefficient of permeability or hydraulic conductivity. Okay. So, once again I can say here the definition of coefficient of permeability or hydraulic conductivity is, it is the ratio of rate of flow of water per unit area of the aquifer under unit hydraulic gradient, and the unit for that is meter per day. This should be remembered to solve the problems. Hello, in the last class we had discussed about Darcy's velocity, and we had got the equation V is equal to minus K into dH by dl, right? The V indicates Darcy's velocity, the K indicates hydraulic coefficient, and the ratio of dH by dl indicates the hydraulic gradient, or it can be called as the variation of the head with respect to the length. Okay, there is a very small problem on this, we shall solve it. I hope you take down the problem. The water table levels in two observation wells 350 meter apart are 210.5 meter, 210.5 meter and 206.25 meter. Full stop. If the hydraulic conductivity and porosity of the aquifer are 12.5 meter per day and 15%, comma, what is the actual velocity of flow in the aquifer? What is the actual velocity of flow in the aquifer? Let us start with the problem. They have given the data of the hydraulic, or they have given the value of hydraulic conductivity, okay, and its value is given as 12.5 meters per day. we can observe it is expressed as meters per day, as the velocity of the groundwater is very low, and whatever the unit of velocity of groundwater is there, that holds good for the hydraulic conductivity as well. Okay. The next is, they have given the data of dl, that is the distance between two observation wells is 350 meter apart, and they have given the value of dH as well, as you can observe in the question. The water table levels in two observation wells 350 meter apart, okay, are 210.5 meter and 206.25 meter. What we should do to calculate the dH? We have to take the difference in water levels, that is 210.5 meter minus 206.25 meters. What is the value of dl? They have given it as 350 meters. Okay. So, the value of the hydraulic gradient dH by dl is, we have calculated it as 4.25 divided by 350. So, we have got the value of the hydraulic gradient. Okay. What we will be doing here is, we will substitute to the Darcy's velocity equation. The K value is 12.5 and the value of dH by dl is 4.25 divided by 350. So, we will be getting the value of V as 0.1518, that is minus 0.1518, and the value or the unit of the V is meter per day. Okay. So, we have got the value of the Darcy's velocity, and in the question they have asked to calculate the value of V actual. Okay. How will you calculate the value of V actual? We have a formula, V actual is equal to Darcy's velocity by the porosity. The value of the porosity is given in the question and it is given as 15%. Okay. So, VA will be equal to minus 0.1518 divided by 15% means 15 divided by 100, and you will be getting the value of VA as 1.01 meters per. Okay. So, you can ask the question, what is the difference between the actual velocity and the Darcy's velocity? The Darcy's velocity is, and the Darcy's equation is based upon certain assumptions, but in actual practice or in the actual field, the velocity of the groundwater will be this much. VA is 1.01 meter per day, that is all. Okay. A very simple problem. This has been asked number of times for the 4 marks. The next we will move on to the next property of the aquifer, or the next measurable property of the aquifer. The next measurable property of the aquifer is the transmissibility, or it is called as transmissivity, or it is also called as transmissivity coefficient. Okay. The next measurable property of an aquifer is transmissivity, or it is also called as transmissibility, or it is also called as transmissivity coefficient. Okay. To know about the transmissivity, we will take an small derivation, take up a small derivation. Okay. I will write a schematic representation of the aquifer. Okay. This is an impermeable membrane at the bottom, and this is also an impermeable membrane. Okay. At the top we have an impermeable membrane, at the bottom also we will have an impermeable membrane. Where does this case appear? As you all know, aquifer can be of two types, that is confined aquifer and an unconfined aquifer. In the confined aquifer, it will be having top impermeable membrane and the bottom impermeable membrane. For the unconfined aquifer, the upper surface will be exposed to free water table and the bottom of the aquifer will be of impermeable membrane. Okay. Look here. So let us take this as thickness T and this as width W, okay, of an aquifer. As you all know, the equation for discharge through an aquifer is given by Q is equal to A into V. Okay, this is the basic equation for the discharge. Let's write the notation. Q is discharge, A is area of flow, V is Darcy's velocity. Okay. Now look here. How will you calculate the area of flow? By looking at the diagram, you can see the area of flow is or can be calculated with the help of this two dimension, that is A equals T into W, where T is thickness of an aquifer and W is the width of an aquifer, right. So we have got all the notations here and we can start with the derivation. The equation for the discharge is Q is equal to A into V. Okay. Q equals, what I will be doing is I will substitute for A, that is T into W. As you all know, V is nothing but Darcy's velocity. We have an equation for that, minus K into dH by dL. So just write in the bracket as V equals minus K into dH by d. Okay, because while evaluating, the evaluator should know how does the value for the V is changed to minus K into dH by dL, that is by Darcy's velocity equation. Okay. after all this you have to write what is K, what is dH by dl also. Okay, what is K? K is hydraulic conductivity and dH by dl is what? The hydraulic gradient. Okay. So what I will be doing is I will be writing this as equation 1, that is the equation for Q. Let us write it as equation 1. What I will be doing next is I will be writing this as equation 2. Next, what I will be doing, look here, we will be assuming the width of the aquifer to be 1. So what we will be doing here is we will substitute 1 for W. So Q will be equal to what? T into 1 into minus K into dH by dl. Okay. So what I will be doing here is I will bring this K to the inside the bracket. So this Q will be T into K minus multiplied by minus of dH by dl. Okay. So just observe carefully here, the product of thickness of the aquifer and the hydraulic conductivity is called as the transmissivity or transmissivity coefficient, and it is indicated by the symbol capital T. Okay. So this Q will be equal to T or minus T into dH by dl, or if you need an equation for T, what I will be doing is T equals Q divided by dH by dl. That's okay. So we got the expression for T as T equals Q divided by dH by dl. You can define the transmissivity as discharge or rate of flow of an aquifer under a unit hydraulic gradient can be called as what? Transmissivity or transmissibility or transmissivity coefficient, or you can simply define it as the product of thickness of the aquifer and the hydraulic coefficient or hydraulic conductivity you can call. Okay. So that's about the transmissivity. The next, the measurable property of an aquifer is the specific retention. Okay.